So let's take a look at the problem of the day results for our Lewis structure practice. So we have three compounds: sulfur dioxide, carbon tetrabromide, and aluminum fluoride. And each one of these has a different type of bonding going on, although two of them wind up being essentially nonpolar overall. First, let's look at the ionically bonded aluminum fluoride. Fluorine is the most electronegative element, so anything it combines with just about will have a strong electronegativity difference, sometimes strong enough to be ionic and other times polar covalent. Fluorine is a halogen and thus needs only one electron shared or taken away to get its octet, and aluminum has 3 valence electrons. So aluminum, being a metal, has a tendency to lose electrons, and these 3 will be lost to each of the each of the fluorines. We can see that the notation in this Lewis structure demonstrates a ionic bond. We don't see covalent lines, and we see charge symbols. The electronegativity difference here is quite polar, 2.5. Carbon tetrabromide. All the individual bonds between carbon and bromine are pretty nonpolar, and so it's not surprising it's going to be nonpolar overall. We see once again the involvement of halogens, bromine, each needing a single covalent bond. Carbon, having 4 valence electrons, needs 4 bonds. So in this case, we'll have 4 single covalent bonds, no dipole symbols, no charge symbols. Silicon dioxide is an example of a compound involving oxygen that may at first appear to have polar covalent bonding happening. And if we were just to take in a literal sense the electronegativity differences here, we would say that there's a significant electronegativity difference between silicon and oxygen. And so we could put the dipole symbols, and as I'm instructing you, just do it if that's what's happening, that's fine. And this would be the correct Lewis structure. Each oxygen has 6 valence electrons, so each oxygen needs 2 covalent bonds. Silicon, like carbon, is a group 4 element and needs 4 bonds total. So oxygen tends to form either single or double bonds, and you see that as the case with double bonding here. And if you do it this way, this is certainly correct. I didn't ask you to actually analyze, more deeply the structure, but I would be remiss if I did not at least mention, because the structure is the same in every direction, so to speak, and in terms of its total electronegativity balance. This is actually an overall nonpolar compound. Silicon dioxide is found a lot in sand, and as you can probably guess, is a fairly inert nonpolar substance. And so once again, this is a case where based on the way that we're looking at individual bonds, it appears to have polar bonds, and you're correct to draw it that way. But overall, when we step back and analyze the compound, we see this balancing here that causes what's called a net nonpolar. Regardless, the correct symbols, if you use them, you got credit. Good luck. Well, actually, congratulations. So.